So, hello everyone. I am Anantal, and today we'll take a session. I'll take a session on on robotic simulations. So, in today's lecture, we'll study about the motivations of why do we need more why do we need robotic simulations. Then we'll see some examples, some platforms which are generally used for simulations like Pybullet or Mojoku, which are Python based, and we have already seen the Simulink based simulations already, so I'll not go through that again. Uh, then we'll study how the universal robot description file looks like, and then we'll see some installation and setup, and then and some examples. Okay, so I'll start with this motivation thing first. Why do we need simulators, right? So if I if I talk about simulators, I'll start with saying that designing controllers for the is a very hard engineering problem, right? And it requires a lot of understanding of the system, and there's a high the systems are highly high dimensional and highly dynamic, right? Plus they also evolve, they change over the time because they break and they degrade all the time, right? So it is very difficult to design controllers for the real life robots. So moreover, then people say that can we use deep learning or reinforcement learning to basically have something that is more model free, and we don't have to rely on the model of the robot, and we simply collect a lot of data, a lot of experience, and then let the algorithm handle the rest. So but the main problem in applying deep learning or reinforcement learning is that we need a lot of data. As you can see, ImageNet has 1.2 million labeled images. Even if you go to machine translation, it has 36 million sentence pairs. And in DeepRL, if I look into the simulations of hovering of a dexterous hand, it also requires something like 38 million time steps. So basically this data is very expensive because first of all the robot is itself is very expensive, right? Then I say that then actually there is a safety constraint that is associated with the collection of the data, right? So if I go ahead and start collecting data on a autonomous car or an autonomous robot, we'll have to make sure that the robot is safe and the people in the surrounding are also safe, right? So there is a big safety constraint which is also associated with the robotic data. And uh, and a big problem is that we have to label the data as well, right? So suppose if I say if my robot chooses a particular colored object, so I have to label the color as well of the object from in the first end for my robot to correctly detect the color, and then pick and drop it somewhere else, right? So labeling is also very expensive. So if I say if I have to label data in the real world, which has a lot of things, a charger or a notebook or pen on a typical study table, it is very difficult to label each of these things because the shape, size, and the color vary a lot, right? So labeling real life data is also very expensive actually. So how do we actually get around this problem of data availability in robotics? So one is either we go out and collect a lot of data irrespective of if it is expensive or not, or we design some efficient reinforcement learning methods that require less data, or we go ahead with unsupervised robot learning. That is, we don't need labeled data in that case, so we can actually eliminate the labeling costs. But uh, can we use simulated data for training the robots. So the advantages of simulated data is that it is very cheap and fast and very scalable also, because you are the one who designs what all things are to be kept in the simulation environment. So plus, since it is inside your computer, it is always safe. uh, like your since the robot, there's no physical robot in the simulation, you can actually have the let the robot crash as many times as you want, so that it can learn an efficient uh, strategy to deliver its tasks, right? Plus there is no labeling cost associated, because since you are developing the environment, you already can label the things that you are placing in the and in the environment. Plus there is no real world probability distributions associated with the things around present in the environment, because you can definitely know that these things are already here. You don't have to worry too much about the probability distributions of things. However, like the people also argue that simulated data might work or might not work, because there are a lot of different disadvantages that the simulation actually has. So it is very difficult to accurately model different sensors and different dynamical physical systems in the real world. Plus even small errors might lead to large control errors. Even if I train my policy or my strategy in the simulation, and there might be a case that even a small error in the sensing in the real world can actually lead to a very large error, right? So this is quite common in robotic systems. Although people try to model the real world as people try to model these simulations as close to real world as possible, but since it is very difficult to model them, and if I start to model these things very properly, it will actually boost up my graphic requirements, which in turn will cost me a lot of money while I simulate. Plus it is very difficult to actually simulate the real world. So people try to actually use the simulated data a lot of times, but then there's a requirement that once you do the simulation, you actually transfer it to a real world robot once, and at least let it test. Even if you're not training it on the real world robot, it is fine, but at least you test it on the real world robot. So this is called sim to real, uh, simulation to real kind of model, which generally people in the uh, in the robotics world use. So apart from sim to real, which I already told you, there are some other advantages of using simulations. So actually you can use simulations to actually design prototype your algorithms, and then actually let it and then check if the algorithms are working fine or not, right? So you don't have to apply your algorithms directly to a real world robot. You can actually just, if you just want to check your algorithms are they correct or not, then directly try them in the simulation, see if they're following the general pattern. Also, if you want to debug some of your implementations, so generally it is a good idea to first implement it on simulation, so that you can actually see if there are some errors in your actual code, or your implementation. Plus you can also study about the prototyping. You can actually study about prototyping the systems, and then you can also test it on the simulations first. So basically this gives you a lot of freedom to actually do robotics and design controllers for robotic systems, since you don't have to rely totally on the hardware, right? So simulation is a good way for any controls or robotics engineer in general to get started with robotics actually, and that too at a very low cost. So yeah, now we have actually seen why do we actually need simulations. So I'll actually go ahead and tell you what different simulation environments that are available around in the world. So there are multiple such examples. So one is Mojoku. So if you can see this screen, this is the official website and the documentation of Mojoku, which stands for multi-joint dynamics with contact. Right. So in a similar, this is a C++ and Python. It is available with C++ bindings plus Python bindings as well, right? In a similar way, and this is actually recently last year, Google's DeepMind actually acquired this and they made it open source. So if you follow this Mojoku program very closely, you'll see that it is evolving very fast in a very fast way, and yeah, you can see very high level of engagement from the community in its documentation and code as well. So yeah, and if I say PyBullet, there's one more simulation environment called PyBullet. So this is also actually owned by Google itself, and it is also an open source simulation physics simulation engine. So if you want, you can go through these websites, and there are a lot of documentations that are available. So you can download the documentation, or go through the quick start guide actually. So this actually covers a lot of these things in great detail. I'll also cover these things in this session, briefly touch these things. Then there is one more simulation environment called as it is actually owned by NVIDIA. So ISEC. So NVIDIA actually allows you to train multi agent systems and use GPUs to actually train your accelerate your training and so that you can train it faster. And even if you can see it in these videos, although my internet is not that good, yeah, so you might see a lot of different quadruped robots being trained at the same time. In a similar way, in this video you can see a lot of dexterous hands are being trained, and in the middle video you can see a lot of robotic arms that are being trained to actually screw these things. So actually this simulation environment actually helps you to uh, use GPUs to accelerate your training faster. So then even if you work with robotic operating system, there's a simulator in by default. There's one simulator called Gazebo actually, so you can also use that. So in today's class, I'll actually so if you can see these robots present in these simulations, they are actually described by a file called URDF, which I'll actually explain you or kind of go in some detail now. So all these simulation environments, they actually have their robots description file in the form of URDFs actually. So sorry. So 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 if you see what URDF stands for is Universal Robot Description File, right? And it is generally used in ROS projects, plus all these simulation environments which I have shown you right now. And it was created by Willow Garage and Open Source Robotics Foundation. And if you want, you can actually go through a detailed tutorial of how to develop a URDF properly in this official documentation and tutorial website of URDF on ROS Wiki, right? But I'll briefly give you an overview of how the URDFs, how you can actually design your own URDF in a very basic way. So overall structure of a URDF consists of different links and joints. So there are different links which are connected by different joints, right? So say if I have a base here, right, and then I have a slider on top of this base, and an arm which is attached to this with this slider, and a camera on top of this robotic arm. So if you see the connection, there's a connection between the base and the slider, which is a sliding joint, right? And between slider and the robotic arm, there's a revolute joint. Between my robotic arm and the camera, there's a fixed joint actually, or as you say, camera joint. You can name anything, but it is a fixed joint because we want it to be fixed. So different type of joints which are commonly used in URDFs are revolute joint, prismatic joint, continuous joint, and fixed joint. So some people actually argue that continuous joint is kind of a revolute joint, right? But we actually say that like they are similar, but a continuous joint is generally used when we have a lot of rotations that we are expecting from the in the simulation. Suppose we have this wheel here, right? We will not expect that it will rotate by certain degrees. We'll expect that that the wheel might rotate by certain rotations, and so the degrees or radians will be very higher in that case. However, in the case of revolute joint, we actually can measure difference radial distances in terms of degrees or radians. So suppose if I have a robotic arm which has certain which cannot go beyond a certain angle, we'll generally describe it using a revolute joint. So the basic syntax of URDF looks something like this, right? I start with the so this is actually an XML file. URDF is actually an XML file, and we start with this robot description. We start with the name and end with this block. So then we go ahead and describe the link itself. So suppose my arm looks something like this, something like an elliptical kind of thing, right? So we have to describe three different properties of the link itself. So how does it look visually, right? What is its origin and what is its material inside visual properties. Then we have collision properties. So where like collision properties actually will include things like the boundary of its collision. So suppose if my shape of the link looks like this ellipse, this orange ellipse. However, I'm just allowed to have certain different geometries for collision. So say I'll like approximate my collision to just to keep the model simple. I'll assume the collision model to be this square, right? So we can actually describe the collision boundary of the link, and then we actually describe the inertial properties of the link, like the mass and the inertia and the origin of the mass, basically. So the joint description actually looks something like this. uh, like we studied about the link description. Now if you see the joint description, you'll see that a particular joint will include a parent link and a child link, right? So if you see this image, each joint is actually connected by a parent link and a child link, right? So parent link is the link which is already present, and we are attaching a newer link with the already existing link using this joint, right? So if you see a slider link in case of the arm joint is the parent link, because a slider is already there in the system. If we go in this order of the flow chart, and then if we want to attach the arm to it, we'll need this arm joint. So for this arm joint, slider will be the parent link and arm will be the child link. Okay. So So we describe the links in this way, and then we actually define the origin of the rotation, or if in since in this case it is a revolute joint, or if it is a prismatic joint, uh, will describe the axis or the origin of the movement of the uh, prismatic joint, right? Then we actually give a lower and an upper limit of the joint, and so it cannot go below 0 degrees and cannot go above pi by 2 radians, that is 90 degrees. Okay. And the maximum velocity that it can achieve is 100 radians per second, and the maximum effort is 100 newton meters. So so this is how we generally describe a particular joint. So if you see, we generally we define these. So my URDF, a typical URDF looks something like this, which has so we'll have to start with making a basic flow chart of the model, then deciding which joints are there for different, which types of joints are present for different connections, right? And then we go ahead and start describing the link and then the joint. There are different things, like if you go ahead and go through the Ross Wiki tutorial whose link I have shown here, you can actually see that uh, you can actually define a lot more things like sensors, or particular position, starting position of the robot, something like that, right? So if you want to explore more, you can actually go through this link, and this is a very good tutorial if you want to go in deep and then study how a URDF file actually generally is made. But generally, if you want to uh, start with basics simulation of a robot, there are a lot of URDF files which are already available. So you just have to go ahead and search for these URDF files, and you'll find them on you can easily find them on uh, GitHub or any other open source repositories which are available. So in a similar way, Mujoku uses a different form of XML, which they call it as MJCF XML, which stands for Mujoku File XMLs. They are also quite similar to this, and they also have this tutorial here in this, which actually explains you the uh, modeling of these MJCF mechanisms. So we'll start with this kinematic tree, as I actually told you in this slide, right? We describe different things. We start with the world body, start with the base, then go to the child class, and then define the link which are attaching to them. And in a similar way, we can actually define all the other things with respect to that. And if you go in deep in this tutorial, you'll actually get a better idea of how these uh, XMLs are made for different simulation environments, right? So so now let's go ahead and see how we can actually install and run some of these simulations on our computer. So if you are using an Ubuntu or a Windows computer, you'll just have to open a command prompt, right? So I'll go to a terminal, or type command prompt in your search button if you're using Windows, right? And open a new terminal, right? And suppose if I say I want to do a Mojoku tutorial. So, so yeah, if you go ahead and see, the first GitHub repo that you can see is this Mojoku tutorial, which is actually developed by me, and the help of some other resources which are available online, right? So you just have to go down and start following these steps. So for that, before you start start following these steps, you'll have to install Anaconda uh, on your system, right? And then you can actually just start ahead and uh, create different Conda environments and install your installations there. And a link to how to install your Anaconda in Ubuntu or Windows is given here in this link. You can go ahead and follow the instructions given in this link. And once you install this, you'll see that uh, there is a bracket available here which says base, right? So we'll have to create a new environment. This is a base environment, right? So we don't want different installations in my computer uh, to hinder other environments. So I actually use Conda environments, which create a kind of a virtual space inside my virtual environment inside my computer, and it actually installs only some particular. It allows uh, uh, some particular installations in that particular particular versions of different packages in that Conda environment, and you can have different versions of different packages in different Conda environments. So we actually start with creating a Conda environment. uh, we can directly copy it from here and press enter. I'll press yes. So a new Conda environment named Mojoku Tute is created, right? So I'll go ahead and activate then this environment. So as you can see, this base has turned into, so I've entered my Conda environment now. Now what I'll do is I'll clone this repository on my computer, right? So I'll go ahead and git clone this, directly paste it here. So So yeah, I already have this on my computer already. So I'll just go ahead and first delete that uh, file here. Okay, and again install it here. Now, as you can see, I've in my home there's this folder called Mojoku tutorial. Now, if you have studied command line instructions, you have to if you want to enter a folder or if you want to enter into a particular folder, you write cd and the name of the folder. So Mojoko tutorial. Right now I've entered inside this folder, right? And once I've entered inside this folder, I'll just write one simple instruction, that is pip install Mojoku. So since in my computer it's already installed, so it is available in this way. But just writing this instruction will actually install Mojoku in your environment, Mojoku Tute environment, right? And then let's run a simple Python file, which is available here. So excuse me. So as you can see here that this environment is running a bipedal robot which is coming down the slope, and I can actually uh, rotate my view and see. This is just a simple two link bipedal robot, a passive bipedal robot. And if you see in this tutorial, we have a lot of different XMLs present. So we have a lot of examples like double pendulum manipulator or double pendulum leg biped or an acrobat or hopper, gymnast, humanoid robot, manipulator, projectile, pendulum. So you can go ahead and try to run all these examples. All you just have to do is go in this run file, right? Sorry. And then instead of examples.biped, you import some other example, and in the XML path you change your path to that particular example. So suppose if I want to import a double pendulum, I just go ahead and import double pendulum from here, from examples, and then change the XML path to instead of biped.xml, double pendulum.xml will actually help you uh, uh, to get a newer uh, to, some different simulations. And then you can actually go ahead and if you see, go ahead and see the examples here, you can actually see that there's a basic controller which is available here, right? So you can actually explore new different kinds of controllers, say reinforcement learning based controller in this, or model predictive controller, or simple PID controller. And then you can actually see how the performance is changing, and you can actually see it in the simulation itself, right? So yeah, so there are different other examples as well, like gymnast, or leg swing, or manipulator, or under actuated pendulum. So you can go ahead and explore all these examples. Plus, if you want to try more examples, you can actually contribute to this to this repo itself. So this is an open source repository for and it can be accessed by anyone. So you can actually download it for free and then run it. And if even if you want, so if you want to contribute also, you can also contribute it by forking this repository, right? And after forking it, uh, you can actually create a pull request to add more files if you are interested in that case as well. So once you are done with this, right, uh, and I've shown you some examples, you can actually go ahead and try more examples, right? So these are all the examples which are available, and there's a uh, installation instructions also available here, right? So this is a Mojoku tutorial. Probably I'll show you one 5 bullet one as well. So yeah, if you see that I have a lot of pi bullet related examples, so you can actually go ahead and uh, explore these repositories as well. So again, even the installation of pi bullet is quite simple. So probably I'll show you that as well, right? So I'll close this and again close this and open a new terminal window. I'll create a Anaconda environment. Follow all the same steps that I've already shown you earlier. Once I've created this, I'll do conda activate EYB, right? And then I'll go ahead and git clone this repo. So yeah, again I already have this. I might already have this. Yeah, I already have this. I'll probably delete it and show it to you. So I got this PyBullet tutorial file. So I'll go ahead and go inside this folder and I right? Once I'm inside this, I'll have to install some basic packages. It will take some time, not much time, right? Then I'll install PyBullet. Since it is already there in my system, so it is showing that the requirement is already completed. Then I'll install Matplotlib, which will help me to make different graphs. Now, if you just want to check your installation if it is correct or not, just go ahead and write Python 3 and then import PyBullet. Since this thing is working, so you've successfully installed PyBullet on your system. Then you'll try Matplotlib. Since there's no issue, we assume that Matplotlib is also imported successfully, right? So, so again in PyBullet we have a lot of different examples. So there's a Python IPython notebook uh, for setting up for torque control and some 3R manipulation and 2R manipulation of the robots, right? So you can go ahead and explore the this repository and different examples which are there, right? And if you have some doubts, you can actually contact me directly on my email ID, which I guess you guys already know, or ask me on Teams, right? And once you're able to do this, you can actually work around with different controllers, try changing different controllers, or try to achieve something which is bit novel. And there are some homework or say assignment files as well which are unsolved, if you see. So you can actually, if you feel confident enough, you can actually go ahead and try out the homework files and try to write the code for following the trajectory in the control loop to follow the trajectory which is given here. So this is for two hour manipulator, I guess. In the similar way, we have the second assignment. If you want to try it out and see if you are capable enough, so this is for 3R manipulator, since this is a 3D trajectory tracking that you have to do. Write a controller to track this 3D thing, 3D path. And this one is based on neural networks. So if you have some idea about neural networks, then you can actually try it out. If you don't, you can actually ignore this homework. So so yeah, so these are the two repositories. I'll also share the links with you, and you can actually go through these examples, and actually you can see if you are able to first of all set up the environment on your computer. And once you have set it up, you can actually then you can see if you are able to run the already developed examples that are there in these tutorial files, in these tutorial repositories, right? And once you do that, you can start making your custom controllers and try out different controllers as well, right? So so with that, I'll actually conclude this session, right? And if you have any doubts, you can actually contact me on my email ID, that is manantayal@isc.ac.in, right? Or contact me on Teams directly or ask it on the Teams group directly, I'll reply that there. So with that, uh, I'll conclude my session, and all the best. Goodbye.